Hi, and welcome to Mr. Carroll's classroom. Today we're going to take a look at the properties of exponents and also determine whether a data set is linear or exponential in nature. So let's go ahead and get started. Okay, so there are quite a few properties of exponents. So in order to organize this, we're going to go ahead and create a grid and we're going to start laying these out. So the first one that we're going to cover is called the product rule. And the reason why it's the product rule is because I have one thing multiplied by another. And both of these have exponents. So if I have a to the m power times a to the n power, then this is equivalent to a to the m plus n. And let's just go ahead and prove this really quick to see how it works. So say, for example, I have a squared times a to the third power. Well, by this property, this should be equivalent to a to the fifth power. Well, let's check it out. So if I went ahead and split this up as a squared is really a times a, right? And if I went ahead and split this up, a cubed, that's a times a times a. And really all of this is a times a times a times a times a. And in this case, there are 5 a's, so this is equivalent to a to the fifth power, which is the same as what our property is. All right, so let's go ahead and go to the next one. Erase that. Next one is going to be called the quotient rule. And so the quotient rule says that if I have a to the power of m divided by a to the n, then that is equivalent to a to the m minus n. And let's go ahead and see how this works, or why it's correct. This basically says if I have, let's say, a to the fifth divided by, let's say, a cubed, then this should be equivalent to a to the 5 minus 3, that's a 3, which is equal to a squared. So let's go ahead and see if we can figure out how to prove this. So on the top, that's a to the fifth, which is really 5 a's. And then on the bottom, we have a cubed, which is 3 a's. And of course, if we have a bunch of things multiplied on top and bottom and they are equivalent, then we can go ahead and start canceling these out. So I'll cancel these a's, and these a's, which leaves us with 2 a's on top over 1 on the bottom, which is just simply a squared, which is what our property told us it should equal. Let's go to the next one. So the next one is the power rule, and it says if I have a to the power of m all to the power of n, then that is equivalent to a to the m times n. So again, let's check and see if we can prove this. So let's just use an example. Let's say a squared all cubed, and according to this property, the power rule, this is equivalent to a to the 2 times 3, which is a to the power of 6. So let's see if we can get that to work out. So I'm going to go ahead and I'm going to separate a squared. So that is a times a all to the power of 3. And anything to the power of 3 is the same thing as that times itself 3 times. And if I knock out these parentheses, because these are all simply multiplication, then I'm left with 2, 4, 6 a's, which is a to the power of 6, which is what our property told us it should be. All right, let's move on to the next one. All right, so the next one is the power of a product. So if I have a times b all to the power of m, then that's equivalent to a to the m times b to the m. And again, let's go ahead and see if we can get this to work out. So I have, I'm just going to use 2. Actually, let's do, I guess it doesn't really matter. I'll just use a and b, I suppose. We'll say b to the power of, let's choose, I don't know, 3 here. And so this property basically says, well, this should be equivalent to a cubed times b cubed. This kind of gets distributed into both since it's a product of a times b. By the way, if this was an addition sign or subtraction sign in here, you could not apply this rule. That's why it's called the power of a product. But anyways, so let's go ahead and see if we can get this to work. All right, so let's see. I have AB all to the power of 3, which is the same thing as AB times AB times AB. And I can go ahead and drop these parentheses. That's really AB times AB times AB. And in this case, if I combine the like terms here, I have A times A times A, which is equal to 3A's or A cubed, and B times B times B, which is equal to 3B's or B cubed, which is equivalent to what we were expecting. All right, let's move on. Okay, so the next one is going to be the power of a fraction. So if I have a over b all to the m power, or power of m, then that is equivalent to a to the m power of m divided by b to the power of m, essentially distributing this in here. So let's go ahead and figure out a way that we can prove this one as well. So let's just do, I guess, a over b again, and we'll do, I don't know, let's do squared. And according to this property, this should be equivalent to a squared over b squared. And let's see if we can be clever about this and get this to work out. I think what I'm going to do is inside the parentheses, I'm going to go ahead and split up the a over the b, because really that could be rewritten as a times 1 over b, right? Oops, make sure we can actually see that, right? A times 1 over b squared. And based on our, well, I guess I could just leave it like this. But it's kind of similar to our last property here. Let's see here. If I have something all squared, then that is the same thing as that thing, a times 1 over b, multiplied by itself. Let's see here, twice since this is squared. So a times 1 over b. And again, these are all multiplications. So I have a times 1 over b. I'll just put parentheses around all of these. Times a times 1 over b. And then what I'm going to do is I'm going to go ahead and combine these like terms here. So this is going to be equivalent to 2a's, which is a squared, times 1 over b all squared. And 1 over b times 1 over b is 1 over b squared, right? So, and actually I should probably put that squared inside of here, right? So a squared times 1 over b squared, and then if I go ahead and just multiply those, I end up with a squared over b squared, and guess what? That is what we were looking for. So we had a little bit of work for that one. We had to be a little bit clever there. All right, let's go to the next one. So the zero exponent. So this is kind of one of those rules that is really fundamental to mathematics, but anything, no matter what it is, to the power of 0 is equal to 1. So it's typically something that students will just memorize, but there are actually quite a few different ways you can look at this to prove it. And they're all different, I would say. And I just use one approach, even though, again, there are probably like 5 or 6 approaches to really show that this is in fact true. Probably one of the simplest approaches is really just using a pattern to show that anything to the 0th power is equal to 1. But again, if you're not convinced by this, I would encourage you to look it up, because there are actually quite a few different ways that you can look at this. Anyways, so let's use a pattern here. So let's say I have like 2 to the 4th power, and then I have 2 to the 3rd, 2 squared, 2 to the 1st, 2 to the 0, 2 to the -1, 2 to the -2, 2 to the -3, and then 2 to the -4. What are all of these equivalent to? And really the one we're after is that one right in the middle here, which is 2 to the 0th power. But let's go ahead and take a look. So 2 to the 4th, if that is equivalent to 2 times 2 times 2 times 2, which is actually 16. 2 to the 3rd is going to be equal to 2 times 2 times 2, which is 8. 2 squared is 2 times 2, which is 4. 2 to the 1st power is 2. Let's skip 2 to the 0th power for now, assuming we just don't know what it is. And let's go ahead and use 2 to the -1st power. Well, and actually, do we have a negative? I guess that's going to be next. But we're going to learn here that to anything to the negative power is you just move that to the bottom, which is, so 2 to the negative first power is 1/2. 2 to the negative second power is 1 over 2 squared, or 1 over 4. 2 to the negative third power is 1 over 2 to the third, which is 1/8. And then 2 to the negative fourth is 1 over 2 to the fourth, which is 1/16. All right, so let's take a look at this pattern, right? So every time we are simply dividing by 2, right? Dividing by 2, and oh, I'm missing this one. And then I want to divide by 2, divide by 2, divide by 2, divide by 2. So what number fits in here? Well, in this case, the number that fits is 1. 2 divided by 2 is 1 to get here, going from here down to here. And then 1 divided by 2 gets you to 1/2, and that pattern continues on. Now, again, if you're not totally convinced with this, we'll call it a proof here, but really we're just visually looking at a relationship, that's okay. I would, again, highly encourage you to look this up and check out other proofs on your own. There are quite a few of them, and they all are fairly straightforward and logical. Okay, so, but anyways, for now we're going to say a to the 0th power, doesn't matter what it is, anything to the 0th power is going to be equal to 1. All right, so let's continue on, get rid of all that work there. Okay, so next is our negative exponent property. So a to the negative m is equal to 1 over a to the m. And let's see here. Is there a way that we can prove this? Let me think about this one. Yeah, so I think what I'm going to do is I'm going to go ahead and try to use another relationship for this one to show how this is true. So for example, let's go ahead and we will use real numbers here, just so that way we have something that we can calculate. So like, say for example, if I wanted to figure out what 2 to the negative third was, well, let's start with 2 to the positive 3, and really I should actually, like, you know what, hold on, let me see, let me bring this back up here. So we already have this work, right? So if I have 2 to the negative third, what I can do is I can really just show this by, let me see if I can get rid of these here. So we'll leave this 1 in here. And let me just grab a different color here. So 2 to the negative third is showing that this is 1 over 8, which is equal to 1 over 2 to the third power. All right, and I guess, again, it's kind of hard to show this, but once you get more familiar with logarithmic and, well, we technically call them logarithmic scales, but then you'll understand a little bit more of the way this works. But ultimately, we are following a pattern here. So for example, 2 to the third is 8, and then if we go down, 2 squared is 4, 2 to the first is 2, 2 to the 0 is 1, and then we get into these negatives. And you can see that every single time what we're actually doing is we are dividing the previous number by 2. That's this like common ratio, or this ratio that we're applying here. So again, if you're not totally satisfied with that, that's okay. You can go ahead and probably look up a number of different proofs with that, but we can definitely see that it is clear with the relationship that each one of these, 2 to the negative third is really 1 over 2 cubed, which is 1/8. Like down here, 2 to the negative fourth, this one right here, actually let me get rid of these so you can see, 2 to the negative fourth is 1 over 2 to the fourth, which is 1 over 16, and so on and so forth. So definitely the rule applies here, okay? All right, so let's get to this last one here. So the last one is called our fractional exponent, and this one is definitely interesting. Let me actually remove, hang on one second, all this work here. And so this one can actually be quite useful, and a lot of students don't don't initially know this, but if I have the square root of x, there is actually another way to write this. First of all, that square root is technically called a radical, and that radical has an index. The square root has an index of 2 up here. We just usually don't write the 2 because it's inferred. But anyway, there is actually another way to write a radical. This is technically x to the power of 1/2. This is a fractional exponent. And if you have like the cube root, or radical with an index of 3, if you have the cube root of x, that is actually can be written as x to the 1/3, and so on and so forth. The fourth root of x is x to the 1/4, so on and so forth. So what we're going to do is we're actually going to apply that here in this rule. So the rule says that a to the m divided by n is actually the nth root of a to the m, or you could even write it like this, the nth root of a all to the m. These are technically, both of these are equivalent. These are equivalent statements. So let's go ahead and see how that looks. And I'm going to use a similar example to the one I just showed. So for example, if I have, let's say, a to the, I don't know, let's use 3/2. All right, if I have a to the 3/2. This rule says that this should be equivalent to the square root of a to the 3rd, or I could write it as the square root of a all to the 3rd. And these are technically equivalent statements. So let's go ahead and see why that works. So I'm going to go ahead and rewrite this exponent as a to the power of 3 times 1/2. I could do that, right? That's the same thing as 3/2, 3 times 1/2. And we're going to apply one of these other rules. Actually, we're going to apply this rule right here, this power rule. If I have a to the power of m times n, then I could have started with a to the power of m to the n, or vice versa. It could have been a to the n to the m, and it would be identical. So let's go ahead and apply those rules. So this could be a to the power of 3 all to the 1/2, or it could be a to the 1/2 all to the power of 3. It doesn't really matter. But what did I just say about something to the power of 1/2? Well, that is the same thing as having the square roots. So I could rewrite this one right here as the square root of a cubed, because a cubed is on the inside of the parentheses, right? And the square root has this little index of 2. We usually don't write that for square roots. And then this one here as well. So I have a to the power of 1/2, which is the square root of a, and then all of that to the power of 3. And again, I can put that little index of 2 there if I want. But ultimately, both of these are equivalent to what our rule is saying it should be equal to. So there we go. All right, let's go ahead and get rid of all that work. And let's go ahead and move on. So there are quite a few rules here: the product rule, quotient rule, power of a product rule, power of a fraction rule, zero exponent rule, negative exponent rule, and fractional exponent rule. And we proved them all, right? We can see that these do in fact work. And even with those proofs, you can see how to use them, which is very cool. All right, so let's go ahead and move on to the second portion of this lesson. And this one is going to be, whoops, hang on one second. I got too much on the screen there. So this one is going to be looking at data sets and determining if that data set is either linear in nature or if it is exponential. Now, I want to be clear to say that data sets could be an infinite number of other possibilities, but we are just only utilizing or going after those two possibilities in these examples. All right, so first example here. Actually, before I go over this example, is just talking about the nature of, hang on one second, just talking about the nature of an exponential function itself. You may or may not know this, but an exponential function takes on this form right here. F of x is equal to some constant a, could be 1 or any other constant, times b to the power of x. Okay, now what is b in this case? B stands for the base, or this common ratio. It's really what we're multiplying our every subsequent number by, essentially. Okay, so and if you have learned about geometric sequences, you could actually substitute this a sub 1 times r to the n or n minus 1, depending on your formula there. But yeah, these are basically the exact same thing, okay? It's just that with geometric sequences, we care about specific discrete numbers, but with exponential functions, we care about all of the numbers, all of the x values that we can plug in, not just 1, 2, 3, 4, but everything in between as well. Okay, so anyways, and let's see, for exponential functions, what do they look like? Well, essentially, if that common ratio or that base is greater than 1, then this thing is going to increase very rapidly by a specific ratio, though. All right, and that ratio happens to be the base. However, if the base is between 0 and 1, meaning the base is some kind of fraction, positive fraction, between 0 and 1, then it is going to decrease like this line here, but they're both going to be these curved lines. Definitely not linear, okay? All right, so let's go ahead and take a look at a couple of examples. All right, so here I have a set of data, and you can see I have some x's and some y's. And let's see, do we have any order for this? -3, -1, 1, 3, 5. So we are increasing by 2 on the x's, and then we have our response variable, our y's. And you can think of these as coordinates. So how do we determine if this thing is linear? Well, if it is linear, then I should be able to figure out the rate of change between any two points, and it should be the same, right? With a linear graph or a linear function, then that rate of change should be constant. So let's go ahead and do that. Okay, so let's just remind ourselves that the rate of change formula for a line or the slope is if I have two given points, x1, y1, x2, y2, then that is going to be y2 minus y1 divided by x2 minus x1. So let's go ahead and apply that. So if I take this point here as my x2, y2, and then this one as x1, y1, and apply the formula, then I end up with this rate of change of -3/2. And let's go ahead and find another one here. And so I'm going to take these 2 points, and I end up with the same exact rate of change of -3/2. And in fact, if you took any combination of points, it doesn't matter what combination there is, then you should end up with the rate of change of -3/2. So what does that mean? Well, it basically means that this function is linear and it has a slope of -3/2. Okay, so that's pretty much all it means, right? But that's what we wanted to determine, whether or not this was linear or exponential. Okay, and by the way, if you did actually graph this function, then you would see, or graph these points, then you would go ahead and see that, yeah, these definitely do form a line. These points would be said to be collinear. All right, so last one here, let's add another data set, and we'll determine whether this is linear or exponential. And we're going to follow the exact same approach. We're going to apply the rate of change formula just to get an idea of what's going on here. And so as I do this, I'm going to take these first 2 points, and I end up with a rate of change of -12. But then the next 2, I get -6. So let's continue and see what's going on here. The next 2, I get -3. And then the last 2, I get -1.5. So the rate of change is different for every single pair of points that I measured, which definitely means this is not linear. But the next question is it exponential? So what does it mean to be exponential? Well, you got to remember that even though with exponentials they are rapidly increasing or decreasing, there is some method to the madness. They are rapidly increasing or decreasing by a common base, or this common ratio. So let's see if we can figure out what that is. So upon further investigation, we notice that the rates of change are actually decreasing or being multiplied by 1/2 as we continue on here from -12 to -6 to -3 to -1.5. So we're multiplying by 1/2. So what does that mean? Well, that basically means that this is exponential, and we have figured out that base, or that common ratio there, which in this case is 1/2. And if you went ahead and plotted these points, you would see that this thing is decreasing as we go along the x, and every subsequent y value is essentially half of the previous y value, okay, which definitely makes this an exponential. All right, guys, so that takes care of this lesson. We covered all of the the properties of exponents, and we also proved them. And we also took a look at just some data sets, really not applying any algebra or anything like that yet, but just getting a feel for what exponential functions look like as far as the points go compared to something like the points on a line. All right, hopefully this was helpful, and hopefully I will see you in the next lesson. So have a good one, and we'll see you in the next one. Bye now.